So today we're going to discuss the second problem on bitwise manipulation and concepts relating to binary numbers. So the problem is called swap bits, and it should be pretty self-apparent that we're just swapping the two bits in a binary number. So the problem statement is given one binary number, we take the ith and the jth indices and we swap the values. And we return the new binary number with the indices I and j swapped. Okay, so just as a quick example, so if we have a 5-digit binary number and we index the binary number uh, the same way as we index array, except that the least significant bit would be indexed as 0 and 1, 2, 3, and 4. So instead of uh, index from the very beginning, like an array, we index from the starting from the rightmost um, bit, which is the least significant bit, and the leftmost bit is the most significant bit, right? So if we want to swap the indices 0 and 2, so we are swapping this index with this index, right? So the result, the function call should return 1, 0, 0, 0, 1, right? So 0 would be on this new position and 1 would be swapped to the least significant bit. Okay, this is just a really quick example. And next we will take a look at a brute force solution. So the idea for the brute force solution is simple. We use two different tricks. The solution is really like it only has like 3 or 4 lines of code, so it's really simple. But the idea we're going to use is going to be really useful in a lot of situations. So the first one is we only swap when the two bits are different. So in the example above, since binary number only has 0 and 1, if the two numbers we want to switch are both 1 or both 0, then we don't have to switch them because the value is not going to change. So in this case, if we are swapping 0 and the first and the second index, the 0th and the first index, then swapping 0 with 0 doesn't change the binary number, so we don't have to do it. So the first thing we're going to do is we're going to use an if statement, use a conditional statement to check if we really need to swap, right? And if we don't need to swap, then we just quit and we return the original number, and that will give a valid answer. And the second idea is, if we need to switch, what do we do to ensure that the two values are swapped? So there's multiple ways that you could do it, but the most elegant and simple way is to directly use bitwise operation. And by that I mean you could convert everything to a string and then just swap the indices of the string, but that would actually be pretty costly if you have a large uh, uh, array of if the binary number is very long in essence. So the idea we're going to use is we're going to use bit masking, and we're going to use the XOR operator that we used in the first video to complete this swap. So let's take a look at the solution code. Right, so we're taking a binary number and a ith and jth index to be swapped. I and j are integers. So this conditional statement checks whether the ith and jth element are the same. So keep in mind that this expression shifts the ith bit to the least significant bit, so that we could extract out the value when we end it with 1, and the same thing with this. So these two expressions are what we do is we extract out the last bit. We move the bit that we want to compare to the least significant bit, so that we could end it with 1 and then end it with 1 would mean, so we could end it with 0, end it with 1, it doesn't matter. As long as they are the same, they should return the same value. So if the ith bit and the jth bit are both 1, then this expression will give you true, and this expression will give you true. If they're both 0, this is false. They're both false. So, and it is only when these two are different that we proceed to swap bits. If they're the same, in other words, if they're both 0 or they're both 1, this conditional statement will hold true. Then we don't have to swap it and we just return x. Okay, and next, if we need to swap, if the ith and jth index contain bits of different values, then we're going to perform a swapping. So what we do here is we use something called a bit mask, and we will show this in live code so that it is more concrete and you know what really is going on. So essentially we create two binary numbers. So the first one is the ith element swapped, the ith element, we create a mask that, so this statement, what it does say, if I is equal to 2, then it's going to shift the, it's going to shift 1, 2 places to the left. So what it returns is, if we shift it by 2, what it returns is, will give us 1, 0, 0 in binary, in binary form. Okay. So essentially originally we have 1, and then we just put 2 decimal places after it, so that it would become 1, 0, 0. And if j is 5, say, so 1 swapped 5 would put 5 zeros in front of it, behind it. So, and the I and j, so these two expressions would yield these two values. And then we're going to OR, this is bitwise OR, the two values. So what it does is OR, as you know, is or when the two sides of the OR operator are different, then we return 1. And if they're both 0, we return 0. And if they're both 1, we return 1. So at least as long as one of them is a 1, we return an 1. And so the OR operator works like this. So we just copy down the two numbers. Then we OR. This will give us 1, 0, 0, and then 1, 0, 0. So you can see that this expression gives us a mask. What it means is we only want the couple places in a long binary number to be flipped on, and the other ones, they're going to be all flipped off. So in this case, all the ones that are flipped off are zeros, and only the two numbers that we're going to change, only the two indices that we're going to change are going to be equal to 1. So this would be really useful that if you only want to deal with certain indices in a binary number, you don't want to deal with anything else, you don't have to change it, just a couple of places that you want to extract out or you want to manipulate, then we would use this masking method to just ignore everything else except the ones that are flipped on. So in this case, the ones here would represent the binary numbers we're flipping on. Yes, and so the last step utilizes the XOR operator. So essentially, so remember what XOR does. It gives a 1 if either is a 1, but gives a 0 if both are the same. Okay, so so then we could just give an example to see what XOR would do. Say in this example we would have 6 digit, yeah. So if this number is 1, 0, 0, sorry, 1, 1, 0, 0, 1, 1. If we're swapping the fifth element with the second element, and we have this as the mask. So this is X, and the mask 1 0 0 1 0 0. Okay, and we're going to XOR the mask. So it's going to look like, if we just write it out, we can see that everything that is 0, okay, so as we can see that since a binary number could only be 1 or 0, we could, and we see that these two bits are the ones we want to swap. So setting the mask like this would allow us to have, in this case, 1 XOR with 1 will give you 0, and the 0 XOR with 1 will give you 1. So you can see that originally this is 1 0, and now it becomes 0 and 1. In any other cases, the XOR wouldn't change the number in that place. So if it is a 1, then it's still a 1. If it's a 0, it's still a 0, right? You can see that now this bit and this bit are swapped. Okay, so the time complexity for this, if you examine the code, we only have a if statement, and these are all constant time. So this is big of 1 in constant time, and the brute force solution is good enough. I mean, you can possibly be lower than big of 1 in constant time. So then this would solve our problem in swapping bits. So just a quick recap. The key idea we learned here is to use the bit masking, and the bit masking blocks out everything else in the binary number except the ones that we want to manipulate. And then we use the XOR. XOR using the bit mask wouldn't change the places where we don't want to change. XOR operator wouldn't do that. And you can see with this example that this number, this number, this number, these four numbers are not changed. And but XOR would change in this case, it would change the bits that we want to swap, because so as you can see here, and then so the XOR would do the purpose of utilizing the mask to get rid of, to not change the bits we don't want to change, and to swap to flip on and off the bit that we want to change.